Hi, welcome to this talk. My name is Marc Gourjon. I'm a PhD student working on side channel resilience, and in this talk I would like to focus on the branch of secret compilation which is targeting side channel security. So this branch is about determining, establishing, and preserving some formal property which is defined over the side channel behavior of a program and targeting specifically this side channel behavior of programs. An example would be observational non-interference, where this behavior, the side channel behavior of this program under consideration must be independent of secret or sensitive data. In this talk, I would like to introduce you to the concept of explicit leakage, which introduces a new construct in a programming language to express the side channel behavior of a program. And in this talk, I will use the leak statement for this purpose. And this gives the ability to separate the semantic specification from the representation of side channel behavior, and in the end allows to facilitate program transformation and analysis. We have used this in a recent work for verifying the security of masking, one countermeasure, in user-supplied models of side channel behavior. Let me quickly recap side channel behavior or side channel leakage. When a program is executed on a physical device, this physical execution causes side effects. Among them are well known the timing of instructions or the timing of memory accesses from cache timing, leakage, resource consumption, for example, the power consumption of computations, or physical radiations like electromagnetic radiation, sound, heat dissipation, and so on. These behaviors are usually defined for formal purposes in the leakage models and is usually a subset of the actual behavior, but it's important that this leakage model encapsulates the whole behavior considered. In this talk, I will focus on data-dependent timing, but just to exemplify the concept of explicit leakage really works for a wide class of side channel behaviors. So on the right hand side, you see a program which takes some value x, multiplies it by a secret value, and writes it to a temporary variable, but does not return anything. As you might imagine, that multiplication by 0 or 1 is significantly easier than multiplying by a large prime number, for example, and therefore the timing of multiplication might be dependent on the operands. So for this instruction here, or this operation here, you can imagine that the time it takes to compute it depends on both values x and the secret value on the right hand side. The point I would like to make is that in practice there is a very large and diverse set of leakage behaviors or side channel effects. These are usually architecture specific or even device specific. One example is the timing of multiplication, where here this table from a cryptographic developer indicates that for older ARM devices, the timing of this multiplication from two 32-bit values to one 64-bit value was timing sensitive, that is dependent on the inputs. Whereas for recent architectures, it's quite okay, except for the Cortex M3, where it's apparently still sensitive to timing attacks. So far this is already a bit diverse, but the fun part really comes with RISC-V, where we have one common instruction set architecture which can be implemented by different communities or vendors, and therefore we might see a lot more diverse side channel behavior. Furthermore, it's not only about multiplication. This is just to exemplify. This also holds for memory accesses, cache architectures, vectorized instruction sets. And think of AVX, ARM, Neon. There are lots of extensions which possibly have distinct and diverse timing or other side channel behavior. This diverse set of leakage behaviors we encounter in practice is a bit in conflict with the goals of secret compilation, which is on the one hand to have good security assurance from the formal notions, and that means that the leakage model must consider this diverse behavior, and on the other hand, the goal of having slightly efficient implementation, which means that on the Cortex M4, the supplied hardware multiplication instructions should be used, whereas on the Cortex M3 it must not be used. And this is also in conflict with the traditional way of modeling these leakage behaviors. In the traditional approach, usually leakage is tied to semantic. That means that in a domain-specific language, every construct or every operator encodes a specific semantic and a specific side-channel behavior. This means to encode the behavior which is different on M4 and M3 for the same multiplication, multiple multiplication operators have to be introduced. So in this example here on the right, I'm showing that with different colors that the same multiplication is performed with operands E1 and E2, and to execute the step, they have distinct side-channel behavior as indicated by the arrow in the middle. That, for example, for the red multiplication, which should somehow ideally be representative for the M3, the operands of the multiplication E1 and E2 impact the side-channel behavior or determine some side-channel behavior. And clearly this is not optimal, because to encode a lot of different diverse leakage effects or leakage behaviors, many operands or operators and constructs are introduced, and each of these variants has to be handled. And also the transformation is always tied to these specific behaviors. There's a way around this, and this is explicit leakage, and brings me to the main topic. So the suggestion here is that we separate the specification representation of side-channel behavior from semantic by introducing a new construct, which I will denote leak. And so on the right-hand side, you see this dedicated construct, leak, which takes a number of expressions. And the idea is that the expressions in the leak statements define or represent the program side-channel behavior. The remaining part of the language can now remain free of side-channel specification and specifies only the semantic behavior of programs. Now, with this dedicated construct, different variants of side-channel behavior can be encoded without introducing additional operators. So if we take again these three distinct multiplications, each with a different side-channel behavior but with the same semantic, these can be now expressed with the help of two statements. One in the second line is always the semantic specification, being that C is being assigned the multiplications result of E1 times E2. And then the different side-channel behavior can be indicated with this dedicated leak statement, which in the first case, in the first column, to say, expresses that the side-channel behavior in this program depends on the values E1 and E2, or the expressions. This is quite flexible, so the behavior can quickly be adopted for the second case, where the behavior, this artificial example, only depends on the second operand, or a third case where there is no data-dependent side-channel behavior, and therefore there is no side-channel specification. The concept is really flexible in encoding different behaviors with just a single leak statement, and that's also the key point of it. There's a single construct to specify side-channel behavior, and all the remaining operators remain free of specifications of side-channel behavior, and therefore we don't need any variants anymore. This will also facilitate the analysis later on. There are ways to abuse this slightly, just to give you an idea, to say that on function return there might be residue on a stack or in a heap, and a dedicated leak statement might be used to say that the side-channel behavior of a program depends on these values left in the stack, if you wish to. The concept is really flexible and applies to a lot of different side-channel behaviors, and also allows to specify, for example, memory leakage, or memory leakage arising from memory accesses. So the meaning of the leak construct, to summarize, is that each expression in the leak statement defines the side-channel behavior of a program, or represents the side-channel behavior of a program. And on the other hand, leak has no side or semantic effect. It's purely meant to specify the side-channel behavior. And the converse is true for the remainder of the semantic, which is purely semantic or side effect specifying, and not specifying any kind of leak statements. To take the question where these leak statements come from up front, this is up to you, or the user of this concept. One way is to insert leak statements during lifting of input program to intermediate representation, or to perform this annotation during the instruction selection. And another way would be to have a dedicated transformation, which is, for example, done by EasyCrypt, where the leakage behavior of a program is extracted and made explicit. The treatment of leak statements is specific to security notions. Think of observational equivalence, which says that the two programs must be exactly equivalent in the terms of their leak statements, which might also mean that the order in which leakages happen must be the same. So in this case, it is not okay to reorder leak statements. Whereas in k-anonymity, for example, which is relevant for masking, the order does not matter, but the number of leak statements is relevant. Something I will just mention here at this point is that it is important to keep the binding of leak expressions, leak statements to their semantic cause, as we will see later on. Let me now dive into transformations and show how the concept of explicit leakage facilitates analysis and transformations. To do this, let me introduce a small domain-specific language which consists of expressions and statements, expressions of variables and multiplications of expressions, and the statements where we have an assignment, so a semantic action, the specification of sidechain behavior through the leak statement, and a special construct to bind two statements to each other. So ASOC is meant to say that that one statement cannot exist without the other. So S1 cannot exist without S2 and vice versa. This is used to keep the binding between leak statements and semantic cause intact. So we can re-specify the leakage behavior of multiplication as we had it before. On the right-hand side of the association here, we have the multiplication being assigned to C, and then on the left-hand side we have a leak statement to encode diverse sets of leakage behavior, which can be altered quite flexibly. As a first transformation, I would like to introduce a liveness analysis path, which computes not only which variables affect outputs, but also computes which variables affect sidechain behavior in a program. And this is quite easy since we have a dedicated leak statement. The analysis can be made aware of leakage and tag all the variables which are used in leak expressions. For the assignment, it is just as in a common case as if there was no leakage behavior in the program represented, because this assignment and the expressions are free of sidechain behavior. And finally, there's this association, which is in this regards just a sequence operator, and therefore the liveness analysis is performed on both statements. Based on this, secure code elimination can be performed. The idea is that elim tags those statements which can be removed. And for the assignment, it's the usual case that if the variable being assigned to is not live, then it can be removed. But for the leak statement, as we want to preserve observational equivalence, it is never removed. Now, if we consider our program, just those two rules would allow to remove the multiplication here on the right-hand side, but would not remove the leak statement. This would be okay for analysis, but since the causing operation is now removed, this might get into trouble if we look at later on passes which come later on, for example, reordering or lowering. So therefore, the ASOC is used to bind leakage and semantic actions, and therefore prevents that one is removed without the other. This can be quite easily be adopted, for example, to remove secret independent sidechain behavior and not preserve observational equivalence. And this is simply based here on taint information to remove leakage when it is not secret dependent. To summarize, the concept of explicit leakage really allows to specify a diverse class of leakage behavior, and the transformations are becoming largely independent of the actual behavior considered. This is quite nice. This is the good part of it. On the other hand, the association between leakage and semantic has now to be maintained, And this, I think, can be improved. Finally, handling of the leak statements remains specific to the security notion. And I think this is just in line with the focus of secret compilation anyway. Thank you.